I'm going to continue now with working through problems from the first chapter of a book called Problem Solving Strategies by Arthur Engel. And I'm working through the problems. There are 60 problems in the first chapter, it calls itself the invariance principle, but it's basically you have to find some kind of quantity to associate with your problem. And once you've found the right quantity, the problem often becomes quite easy. Not always, but certainly easier. And in the last video, I solved a problem, but it took me 45 minutes or something. But the actual solution takes about 10 seconds to explain, well, a bit more than that, maybe sort of 2 minutes to explain. So I was slightly kicking myself at the end of it and wondering, during the video itself, I thought, was there any way I could have noticed this sooner? And I couldn't think of a way. But I've reflected on it a bit more. So before I try some new problems, I just want to think very briefly about, or talk a little bit about how I might have found the solution to the last one more quickly, in the hope that by discussing that, future problems I will be able to find more quickly. So one of my aims here is to see whether by just working through lots and lots of these problems I can actually get better at them. And each time I take a long time, I sort of feel, okay, I haven't got there yet. Of course, in the nature of a good set of problems, it should be a bit like that. Just as you think you're getting a bit mechanical, it sort of throws you something from left field, and you find that you need an extra idea or an extra bit of problem-solving savvy that you haven't yet developed. Anyway, so the problem was, if you take the numbers from, if basically a1 up to a2n is a permutation of 1 up to 2n, show that ai plus I can't all be distinct mod 2n. Now what I should have done, I think, is so what puzzled me there was I couldn't see how invariance came in at all, and actually that I think was my mistake, because I can just say I've got a sequence. What do I know about it? I know, I'm assuming that it's a permutation, so I know that these numbers are the numbers from 1 up to 2n in some order. And here I could say I don't actually know that, because but here I could say, supposing I've got another sequence such that bi plus I are all distinct, I equals 1 to 2n, of course distinct mod 2n. I'd like to show that my sequence a1 up to a2n is not the same as my sequence b1 up to b2n. So that was where the way I could have thought about it but didn't. Instead of focusing on a sequence that's definitely a permutation and proving that these numbers aren't all distinct, I could have done it the other way around and said, let's assume that these numbers are all distinct and prove that the bi's are not a permutation. So then what am I trying to do? I'm trying to distinguish between sequences that are permutations of 1 up to 2n and sequences that have this property, that the bi such that bi plus I is a permutation of 1 up to 2n. And so what I would like then is maybe to find an invariant, so some quantity I can associate with a sequence that will be the same for all permutations and will be different for all sequences with this property. And then I could have said to myself, well, what would be a natural source of invariance? It might be, just as I did with another question, I just said, well, let's just see what happens if we take something of that form. And it would be very natural, since we're looking at mod 2n, to say mod 2n and for the lambda i's to be integers. And then we notice that if we want this to be an invariant, in other words, supposing we actually want it not to change, or to be the same for all permutations, then I'd better have the lambda i's all being equal. Is that absolutely true? I suppose if two of them differed by n, then when I swapped, I would, I think, add n to one thing, and yeah, so maybe, but that's a little bit artificial. let's just, it seems very, very sensible at any rate just to choose them all to be the same. And if we're going to choose them all to be the same, I might as well choose them all to be 1. So that would say, let's look at sigma ai mod 2n. And then if you've seen what the solution was, I think I won't do it again, but if you just do look at this quantity, you find that sigma ai mod 2n, because it's a permutation, turns out to be congruent to n. And then here, because these are all distinct, we get that sigma bi plus sigma I is also congruent to n, but sigma I is congruent to n, and so the whole thing doesn't work. In other words, we get the sigma bi is actually congruent to 0 mod 2n. So the two must be different. So I'm not interested in what the solution was. I'm interested in how I might have found it more quickly, and this was where I got to. There was in fact a way in which I could have stopped myself doing a whole lot of sort of little calculations and trying things out and so on, that in the end didn't really help me all that much. Although somehow they helped me in the sense that eventually they led me to have a sort of, unfortunately, slightly sort of aha-ish moment and solve the problem, but it took a while. So I'm going to have that thought in my mind when I look at the next problem. Says the following: the n holes of a socket. Goodness, what is a socket? The n holes. Oh, I see. Just something you put a plug into. So the n holes of a socket are arranged along a circle at equal unit distances. Goodness, is that going to be important? I suppose it is. And numbered 1 to n. For what n can the prongs, I like this, I don't see what the of a plug fitting the socket. I still have no idea what this question is going to be. Be numbered, okay, such that at least one prong in each plugin I'm not sure I'm going to be able to work out what this means. Goes into a hole of the same number. Might have to think a little bit about what this question means. Brackets, good numbering. So I don't yet understand this question, but I will think about it and see whether I can make sense of it. So I think this unit distance is not very important. It just means that it's regularly spaced around a circle. So oh, I see. A plug-in just means a method of plugging in the plug, of which there are n methods. So I think we can number these holes of the socket 1 to n in any order, because the ordering of these things doesn't matter, I think. So we have 1, 2, 3, 4 up to n, because yeah, if I just permute these numbers, I can permute the numbers on the prongs of the plug in the same way. So I might as well just go in a sensible way, 1 up to n like that. So now I want to find some other ordering. So I've got 1, 2, so it seems sort of somehow similar to the previous question. So I want to number the A1, A2, A3 up to AN. And I want to, perhaps I could, yeah. So now I want, I want it to be the case that for all k, if I look at AK plus 1, AK plus 2, up to AN, A1, all the way up to AK, there will be at least one equality between an AI and the J that lies directly above it. Let's try and say that more mathematically. The statement I want is that for all k, there exists m such that a k plus m equals m, and this k plus m is meant to be mod n. Can I write that in a slightly different way? I can, and I think I prefer to do it this way so that am equals m minus k. Yeah, that feels nice, a nicer way of writing it. And that's m minus k mod n. For which n is that possible? I think, although I am really going to try hard to think of an invariant, and I would rather just try to work out what the answer to this is before I get started. So supposing there are just two holes in the socket, then with a plug, if I have a 1 in the right place and a 2 in the right place, then when I plug it the other way, 2, 1, I'm not going to get anything. So 2 does not work. I'm guessing that 3 works, but let's just try it. So 1, 2, 3. So I'll have a 1 there. I better not put a 2 there, because I've got to have exactly one such m, because the number, so each am is only going to give me the right m minus k for one value of k, and I've got to have it happening for n different values of k, and there are only n of these things, and so it's got to be the case, in fact, for all k, that there exists a unique m. If this is true, it's got to be unique. So I mustn't have a 2 there, so I must have a 3. So I put a 2 there. I'm guessing this is going to work. So 3, 2, yes, if I shift it that way, and then if I shift it even further, or shift that, I get the 3. So 3 is a tick. I'm guessing, I'm sort of assuming it's going to be essentially the same answer as last time. I bet 4 will not work, but let's just try it. 1, 2, 3, 4, 1, 3, so I mustn't have a 4 here, because then it would work. It really does feel almost exactly the same as the last question, so let's just see whether that's really the case. So for all k, there exists a unique m such that am minus m equals minus k, but I might as well say k mod n. I've just changed my variable from k minus k, from k to minus k. So that's just saying that each diagonal is hit exactly once. And so it really is the same as the last question. And therefore n can't be even. So n must be odd, and I think if n is odd, I need actually to prove that it can be done when n is odd. Is that likely to be difficult? I sort of feel, okay, let's just quickly try to do that. I'll have a look, I'll have a go mod 5, that feels big enough to be reasonably so I haven't really explained why n can't be even, so I'm maybe a little bit assuming that you've seen the previous video or followed the proof that I mentioned at the beginning of this one. So I want to, I'm interested in numbers am minus m is constant, in lines that are constant. So these are diagonals, except they're sort of mod 5 diagonals. So for example, that, and that would be one of the diagonals. So if I want to hit each diagonal exactly once, but I also only want to be once in each row and column, I wonder whether I can just do it in a very easy linear way by going knight's moves like this. So 1, 2, 3, and like that. Does that work? I think it does. It seems to work. So let's just see whether that works in general. If I look at, and actually this seems very plausible. So if I look at the set of points of the form x, 2x mod n, if n is odd, so if n is even, this doesn't work because 2x will start repeating itself. It'll only take even values, and there are only n over 2 of those. If n is odd, that's not a problem. And what do we get for am minus m? We get 2x minus x, which is x, which does indeed take different values. So I think I've established that n must be odd, and I think we've answered that question. So I don't feel as though I don't feel too pleased with myself, because it was so closely related to the previous question that the experience gained on the previous question applied very directly. So I don't think I could necessarily say that in any sense my ability to solve these sorts of problems has noticeably improved. But let's keep going. All right, this one looks very different. A game for computing GCD AB and LCM AB. You start with x equals a, y equals b, u equals a, v equals b, and move as follows. If x is less than y, then set y to be y minus x. a slightly unusual notation, at least maybe it isn't, but I don't know it. And v to be v plus u. And if x is greater than y, then set, I suppose it'd be the other way around, x to be x minus y, and u to be u plus v. The game ends with x equals y equals GCD AB, and u equals O. U plus v over 2 equals LCM AB. Show this. I have a feeling this is going to be rather easy. I think writing out the question may be the hardest part of this, but let's just see whether that's a fair comment. So we'd like an invariant. Just one comment, by the way, is that let's just have a quick look at just what happens with x and y. So supposing we started with 3 and 11, that's x, y, then we're always going to subtract the smaller from the larger. So that'll go to 3, 8, and then it'll go to 3, 5, and then it'll go to 3, 2, and then it'll go to 1, 2, and then it'll go to 1, 1. And what we see is that we're just doing Euclid's algorithm, but in a slightly slow way. So instead of subtracting the largest multiple of 3 that's less than or equal to 11 in one go and getting us down to 2, instead we are doing it in steps, we're subtracting 3 once enough times until we've achieved that. So this is doing Euclid's algorithm. And this is sort of somehow mirroring it in the opposite direction in some sense. But anyway, that proves that x and y are going to end up with the greatest common divisor. We'd like to show that u plus v over 2 ends up at the lowest common multiple. So if we could show that so x equals y, I think that's, I have this hunch that it'll also end up with x plus y over 2 being the greatest common divisor of AB. So I'm sort of wondering whether the quantity x plus y, so that means that when it ends up, we'll get that u plus v times x plus y will be 4 times the lowest common multiple times the greatest common divisor. So what I'm hoping is that x plus y times u plus v will be an invariant, and that it must start as 4 times as starting at 4ab, because the lowest common multiple of AB times the greatest common divisor of AB is just A times B. So does it start like that? Well, something funny here. So what does it start with? We get a plus b over 2 times a plus b over 2. Oh, we get a plus b squared, rather. at the beginning, which is not the same as 4ab, so something's not quite right there. So maybe I want to do something a little bit strange. So how can I get no, I've got I want to try to be systematic, so I want to try to find something that is preserved. So I want to find some function of x, y, u, and v is the same as f of x, y minus x. I'm doing this case here, so u, v plus u. So what could be preserved when I do that? Or is it just the lowest common multiples and highest common factor? So I know that the highest common factor of x and y will be preserved when I do that. But it doesn't seem as though the lowest common multiple would be preserved. But am I being, is that just wrong? Well, I do know that the highest common factor of u and v will also be preserved when I apply this process. But okay. So I'm going to try going back to this 311 thing. I think I do need to do some experimenting. So 311. What happens when I do this? So I get 3, 8. And the rule is that if I subtracted the first from the second, then I'll add the first to the second over here. So I get 3, 14. So the sum of all these things is remaining constant, it seems, but that's a bit weird. 3, 5 is going to become 3, 17. 3, 2 will be 3, 20. 1, 2 will become 23, 20. And then 1, 1 will become 23, 43. And if I add those two, I get 66. So I get 33. So average 33. What was the lowest common multiple of these? It was 33, but the lowest common multiple of these was absolutely not 33. It went up to 42, 51, 60. I mean, the lowest common multiple is just absolutely huge. So, but that's not the point. What happened to the my comment about the sums being preserved seems to be a bit irrelevant. It just happens that when we started with 3 here, but when we get to this stage, we subtracted 2, but we added something much bigger than 2. But what? So I'm still wanting to find a quantity that's preserved. So maybe I can focus on what happens when I go from 3, 2 to 1, 2. And 320 to 2320. Doesn't seem as though very much is being preserved there. Um, okay. How can I search for something systematically that is preserved? What sort of quantity is it going to be? That's what's puzzling me. Um, what if I took the highest common factor on this side and multiplied it by the average on this side? Is that going to work? Probably not. No, because the highest common factor is preserved all the time, and the average is not being preserved. Indeed, the average is going up. Perhaps if we just try a slightly different thing, or could we go backwards? That sometimes helps. So if I go backwards, am I doing Euclid's algorithm? Probably not, but I might just have a look. So I subtract 23 from the 43, then I subtract 20 from the 23, and I subtract 3 from the 20. So I am actually, as I go back, subtracting the smaller from the larger. That's sort of interesting. So that tells me that I'm in some sense doing the opposite process. So what would I then want to do? Supposing I think I can without loss of generality, because the whole thing is linear, I'm going to assume that the two numbers I start with are co-prime. So if I started with 1, 1, and over here I started with st, now I apply Euclid's algorithm, and every time I subtract I've got to be careful. So if I subtract the first from the second, then here I add the first to the second. If I subtract the second from the first, here I add the second to the first. That works. So it's exactly the process that was described before, except now I'm starting with two different numbers. And what would I want to prove if I did that? So from here I would go down to 1, 1 eventually. And from here, what would I do? Perhaps I'd end up back at st as I undid the Euclid's algorithm. In fact, that is going to be, well, it will be the case here because this 311 equals that 311. So if I carry on this process, I am actually just doing that. So that very, very strongly suggests that there is some invariant involved. What was it we wanted to prove? That, yes. just don't, I still don't see. Okay. Somehow the highest common factor doesn't feel as though it's can be involved in an invariant. I mean, it is invariant here, but and on this side as well. But what I want to know is how big these things are, or how big their sums are. And what I slightly don't understand is what's going on in the intermediate stages. So here I've got a sum of 23. What's that got to do with this 3 and this 2? And this number, and the sum here was 66. So I've got, let's write it now. 3 and 11 is associated with 14. 3 and 8 is associated with 17. 3 and 5 with 20. 3 and 2 with 23. 1 and 2 with 43. And 1 and 1 with 66. But is there anything, how would I make an invariant out of all that? How can I make 66, for example, out of 3, 11 and 14? There doesn't seem to be a very obvious way. But if I want to make 66 out of those ones, I could just take 3 11s plus 3 11s. Ah, does that work? It's slightly annoying if it does. 3 times 2 plus 3 times 20 does make 66. 1 times 2 plus... Ah, that does not make 66. Because multiplying 23 by 20 is absolutely huge. If I take If I take 11 times 3 plus 3 times 11, I get 66. Is that going to work? 8 times 3 plus 3 times 14. This feels better because the products are not going to get huge because the numbers on here are getting smaller. So what about if I have 1 times 20 plus 2 times 23? That does make 66. 3 20s is 6. Yes, okay. 3 17s 51 plus 15 66. I found my invariant, unfortunately, by pure guesswork. Let me just see whether that really works. So my proposed invariant is xv plus yu. And so if I replace x by x minus y, so I want that x minus y, and then u by u plus v, and I've subtracted yv and I've added yv, and similarly the other way around. So that gives me that if they're co-prime, we'll get that the final thing that we get, that s plus t, is going to equal the initial, because I originally set them as A and B, so it'll be AB plus AB equals AB over 2. That was in a case where they were co-prime, in which case the LCM is just the product. Could I have spotted that in some cleverer way? Let's go back to this. This is what I wanted. So I wanted that if I subtract x from y and I add u to v, I'll get the same number. So had I said to myself, what about a polynomial in x, y, u, and v? And thought about sort of relatively simple polynomials, I would see that if I'm subtracting an x from here and adding a u, it would be quite good to multiply this by a u and multiply this one by an x. And then, yeah, I think I could have done that more systematically, but anyway, I got there in the end. And I think I can't decide whether to do another problem. I think I'm going to keep this as a short video, so I'm going to stop. And I mean, shortish, it took me quite a long time to get there in the end. So thank you for your attention. There will be more of these, and I hope I will become more systematic. So I do feel I am now learning from these examples. It's just that the learning isn't quite paying off yet.